Welcome back everyone. In this chapter, we're diving into network address translation. Today we'll break down how NAT works, the different types including static NAT, dynamic NAT, and PAT, and we'll look how to configure them on a Cisco router. By the end of this chapter, you'll not only understand the theory, you'll know how to implement it for the CCNA exam and in real-world enterprise networks. Before we get started, I just want to say a genuine thank you to everyone who follows the series, watches the videos, leaves comments, and supports the journey. Seeing people learn, grow, and level up their networking skills is exactly why I started this. Your support means more than you know, and we're only getting started. How do private network devices access the internet? Network address translation enables communication between private and public networks. In this chapter, you'll learn the challenges of IPv4 address exhaustion, how NAT works, the different types of NAT, how to configure port address translation, static NAT with port forwarding, and dynamic NAT. By the end of this chapter, you'll understand how to implement NAT on a Cisco network to provide secure and reliable internet connectivity in an enterprise environment. One of the biggest challenges with IPv4 is address exhaustion. IPv4 uses 32-bit addressing, which provides approximately 4.29 billion public IP addresses. While that sounds like a large number, it is not enough for today's internet. With billions of smartphones, computers, IoT devices, and servers connected worldwide, the number of internet-connected devices exceeds the number of available public IPv4 addresses. To solve this issue, RFC 1918 defines three private IPv4 address ranges that are used inside private networks, are not routable on the public internet, and can be reused by different organizations. These private ranges allow organizations to assign internal IP addresses without consuming public IPv4 space. The Internet Assigned Numbers Authority designated these ranges as private and non-routable. Internet service providers block them from entering the public internet using security mechanisms such as access control lists. Since private IPv4 addresses cannot be routed on the internet, how do internal devices access external resources? This is where NAT comes in, enabling private devices to communicate with the public internet. Devices using private IPv4 addresses cannot communicate directly on the internet. To access external networks, they rely on network address translation. NAT allows a router to translate a private IP address into a public IP address, enabling communication between private and public networks. Imagine PC1, 192.168.1.10, private IP, then the web server, 23.10.104.199, public IP, and then you got router public IP, 209.65.1.2. So the process, PC1 sends traffic to its default gateway, the router. The router inspects the layer 3 header. Since the destination is public, the router translates the source IP from 192.168.1.10 to 209.65.1.2, and the packet is forwarded to the internet. When the response returns to 209.65.1.2, the router reserves the translation and forwards it back to PC1. External devices never see the private network. They only see the router's public IP. The primary purpose of NAT is to conserve public IPv4 address space. Instead of assigning a public IP to every internal device, an entire organization can share a single public IP address, just like your home router does. The key advantages of NAT: it conserves public IPv4 addresses, allows use of public IP pools for load balancing, hides internal RFC 1918 addresses, and lets organizations maintain consistent internal addressing. The disadvantages: adds processing overhead and slight delay, and this can impact VoIP, breaks true end-to-end addressing, complicates troubleshooting and traffic tracing, and can interfere with VPN technologies like IPsec. NAT solves the IPv4 exhaustion problem for private networks, but it introduces trade-offs that network engineers must understand. When configuring NAT on a Cisco router, we must understand how the router identifies which addresses belong to the private network and which belong to the public network. By default, a router simply sees two different IP networks. It does not automatically know which is inside or outside. We must define this during configuration. To understand NAT, we identify two main perspectives: inside, the private internal network; outside, the public external network, internet. If PC1 sends traffic to a public server, NAT terminology becomes important. Cisco NAT uses 4 key terms: inside local, the private IP address of the internal device before translation; inside global, the public IP address representing the internal device after translation; outside local, the destination IP address as seen from the inside network, usually the same as the outside global address; and outside global, the actual public IP address of the external destination device. In most basic NAT scenarios, the outside local and outside global addresses are the same. So NAT operation. PC1 sends traffic to the public server. The router identifies source and destination. Since the destination is public, NAT translates inside local, inside global. The packet is forwarded to the internet. When the response returns, the router reserves the translation and forwards it to the original internal device. Key takeaway: NAT works by translating the inside local address to an inside global address when traffic is destined for a public network. Understanding these 4 address types is critical for configuring static NAT, dynamic NAT, and PAT correctly on Cisco IOS. There are 3 primary types of NAT used on Cisco IOS routers: static NAT, dynamic NAT, and PAT. Each serves a different purpose in real-world networks. Static NAT creates a permanent one-to-one mapping between an inside local address and an inside global address. This is used when an internal device must be reachable from the internet. So here's an example: the private server 192.168.1.10 mapped to public IP 209.65.1.2. Internet users access 209.65.1.2, and the router forwards traffic to 192.168.1.10. The key characteristics: mapping does not change, allows inbound connections, and common for servers. So here's a basic configuration: interface, inside interface, IP NAT inside, exit. Interface, outside interfaces, IP NAT outside, exit. IP NAT inside source static, inside local, inside global. Dynamic NAT translates private addresses using a pool of public IP addresses. How it works: a pool of public IPs is configured, inside devices are translated on a first come first served basis, and translation lasts only for the duration of the session. Here's an example pool. If 4 public IPs exist, only 4 internal devices can access the internet simultaneously. The key characteristics: uses ACL to define which inside addresses are translated, translation is temporary, and pool exhaustion can occur. A useful command: clear IP NAT translation. And basic configuration: interface, inside interface, IP NAT inside, interface, outside interface, IP NAT outside, IP NAT pool, then the pool name, the start IP, the end IP, net mask, and subnet mask. IP access list, standard, ACL name, permit, network, wildcard mask. IP NAT inside, source list, ACL name, pool, and pool name. PAT allows multiple private IP addresses to share a single public IP address using port numbers. Most common type of NAT, used in almost every home router. How it works: router translates inside local IP, single public IP, uses unique TCP UDP source ports to track sessions, and each session is identified by IP plus port combination. If 2 devices use the same source port, PAT assigns a new available port. So PAT configuration methods. Method 1, this is PAT using a pool, IP NAT inside source list, ACL name, pool, pool name, and overload. Method 2, PAT using a single interface IP, and this is most common, IP NAT inside source list, ACL name, interface, outside interface, overload. Port forwarding, used to forward specific services, such as HTTP or SSH, to an internal server. An example: forward TCP port 80 to internal web server. And configuration: IP NAT inside source static TCP, inside IP, local port, public IP, and global port. Here's a quick comparison. So we have type, mapping type, public IP usage, inbound access, common use. So static NAT, 1-to-1, 1 per device, inbound access yes, and common use is servers. Dynamic NAT, many to many. The public IP usage, limited pool. Inbound access, no. Common use, small enterprise. And PAT, many to one, single IP, inbound access no, and commonly used on home networks. Here's an exam tip. Static NAT equals permanent mapping. Dynamic NAT equals pool-based temporary mapping. And PAT equals overload using ports, most common. Summary. In this chapter, we explored the critical role that network address translation plays in modern private networks. NAT enables internal devices using private IPv4 addresses to communicate with the public internet while conserving valuable public address space. You learned why IPv4 exhaustion makes NAT necessary, how NAT operates and its key terminology, the differences between static NAT, dynamic NAT, and PAT, and how to configure each type of NAT on a Cisco IOS router. By completing this chapter, you now understand both the theory and practical configuration of NAT in an enterprise environment, an essential topic for real-world networking and the CCNA certification. In Chapter 10, we will move beyond NAT and begin configuring core network services such as NTP, DHCP, and other important IP services within a Cisco environment. I hope you enjoyed this video. I'm CyberEd, and I'll see you in the next chapter. Peace.